Hello everyone, thank you for coming in today. So what's going to happen today is we're mainly going to cover, or the focus is going to be on a past paper. It's going to be the 2020 past paper. And I'll cover question 1 and 3, and then Farhan will come in and cover question 2 and 4. And along with the past paper questions, I'll just cover a bit of content just to give you guys a brief before we go to the questions. So 2020 question 1, the topic is phase relationships. So I'll go through a bit of revision on phase relationships first. So, sorry? Is this better?
Yes.
Alright, I'll bring it down. Can you guys see me? Yeah? Okay. So some of the main ratios you're going to be using for phase relationships are these ones here. Void ratio, porosity, degree of saturation, water content. I'm going to rush through these because you guys have these in your notes and lecture slides, but let me know if you guys want to copy anything down at any point. So void ratio, porosity, and some definitions that are commonly used. You have density, which is mass over volume. A common value you would want to use is the density of water. So that's always going to be, depending on what your units are, 1,000 kilograms per meter cubed or 1 ton per meter cubed. Unit weight is pretty much your density times gravity. So relationship of that is weight divided by volume, and that's always 9.8 kilonewtons per meter cubed. And then specific gravity, so this one is a ratio between your solid density or solid unit weight and your water density or water unit weight. And that's always, in this course, unless specified otherwise, it will always be 2.65. Alright? Some extra derivations are over here, but you won't really use them too much. I'd say the most common one is this one here, ESR equals WGS. What that means is the void ratio times the degree of saturation is equal to the water content times the specific gravity. And something that you use quite often as well is when you're dealing with saturated soil, you let SR equal 1. So when it's saturated, SR equals 1. When it's unsaturated or dry, SR equals 0. So when it's saturated, you can use a relationship E equals WGS. And then you've got some other relationships here, but they're not as commonly used. And another situation is if you're not given any masses or volumes in the question, you can assume that the volume of solids is equal to 1. So when you do this, there's a whole bunch of new relationships that come about. So you can get that the total unit weight is equal to this right here. Or you can get the void ratio to equal that. And some unit weights that you come across as well, your saturated unit weight, your dry unit weight, and your submerged unit weight. So when you use these, saturated unit weight is essentially just your total unit weight under the water table. So you know when you get a soil layer, you have a certain water table, right? And below that water table, the soil is saturated. So you would use gamma sat as a total unit weight. But above that water table, you would use gamma dry. Alright, so did anyone want to write anything down from that page at all? Yeah? Take your time. Take photos. But these notes are also available on a Google Drive, which I'm pretty sure you guys will have access to. We're good? Alright. So we'll get started with 2020 question 1. So this one says, in a project, silty soil is to be excavated from a borrow area and used as fill. We have a test pit with a volume of 2 meters cubed excavated in the borrow area. The total mass of soil excavated was 3.8 tons and it has a moisture content of 5%. So we'll take, normally we'll use your Z ID here, but we'll take omega to be 0. So water content is 5%. The soil from the borrow area is to be moistened at 20 kilograms to each ton of wet soil excavated before it's put into the fill. The compacted fill is to have a void ratio of 0.6. So pretty much whenever you start these questions, always try and visualize what's happening. So it's saying that you're excavating soil from a borrow area. So imagine you had some untouched soil pretty much, right? This is a borrow. And you're excavating soil from there and you're putting it into a fill. And what you're doing is pretty much you're adding some water to the borrow soil before you put it in the fill, and then you compact it after you put it in the fill. So what information you're given here is you're told you have a test pit with a volume of 2 cubic meters excavated from the borrow area. So when they say test pit, that means this is just like a small area that is used to kind of calculate the properties of the soil. So when you have a test pit, imagine you have a little test pit here, that's with a volume of 2 meters cubed. What else are you told? You're told the mass is 3.8 tons. And you're also told the water content is 5%, right? So what can you calculate using those parameters? If you're given mass and volume, what can you calculate from that? Anyone have any ideas? Density, exactly. So density is equal to mass over volume, right? So that here is equal to 3.8 tons divided by 2 meters cubed, which is 1.9 tons per meter cubed. So we've got the density of the soil. What else can we do using the water content? So water content means mass of water divided by mass of solid, right? So mass of water divided by mass of solid, we're told, is 5% or 0.05. That means that mass of water is equal to 0.05 times your mass of solid. Right, so that's a relationship. Whenever you're given water content, always try and derive a relationship between mass of water and mass of solid. So we have that, and that was all from a test soil. So keep in mind, we don't have to worry about that test pit anymore. That was just to give us some information. Now the question's asking, so part A is asking, if 10,000 meters cubed of compacted fill is required, what volume of the silty soil must be excavated from the borrow area? So that means if you're excavating 10,000 from the, if you need 10,000 in the fill, how much do you need to excavate from the borrow area in order to get that, right? So phase relationship questions always need phase relationship diagrams. So if we just draw, so we have two scenarios, right? One from the borrow and one in the fill. So what we're told so far is that from the borrow we have a certain volume that we excavate, and some information about the borrow is that we know the density is 1.9 tons per meter cubed, and we know the relationship between mass of water and mass of solid. So we can just write that down here really quick. So this mass of solid and this mass of water is equal to 0.05 mass of solid. And in the fill area, we're told the total volume is 10,000 meters cubed. So we're excavating from the borrow, we're putting it in the fill, and that's 10,000 meters cubed. That's the total volume of the fill. Alright, and what else are we told about the fill? We're told that the compacted fill is to have a void ratio of 0.6. So here we know that E equals 0.6. So using that information, we can pretty much say E, which is the void ratio, is equal to VV on VS, right? And so just like we did with the water content, where we derived a relationship saying mass of water is 0.05 ms, we can do the same here. We can say that VV is equal to 0.6 Vs. So now we have some relationships and we've set up our phase diagrams. We can start moving on to finding the amount of borrow soil needed. So for that, the game plan here is pretty much you want to find something using the information you're given to go back to your borrow and find how much the total volume from there is required. So what you're told about the fill can be used to find information about the borrow, because one thing that stays constant in both the borrow and the fill is a mass of solid, right? If you were to take some soil from an untouched soil place and then you compact it, or you add water and you compact it, the mass of solid remains the same the entire time. So we can find the mass of solid from the compacted fill, and then we can work backwards to find the rest of the masses and the volumes from the borrow. So to find the mass of solids in the fill, we'll start with after compaction. So we're working backwards here. After compaction, we know that the total volume is 10,000, right? And total volume is equal to what? What is the total volume comprised of? It's comprised of the volume of the voids and the volume of the solid. So that's VV plus VS. And we already have a relationship relating VV and VS, right? We're saying that VV is 0.6 VS. That means that's equal to 0.6 Vs plus Vs. So we get all that in terms of Vs. So that means we have 1.6 Vs is equal to 10,000, which means Vs is equal to 10,000 divided by 1.6, which is 6,250. Alright, so now we have the volume of solid in the fill area, but we're looking for the mass of solid. So we have the volume, we want to find mass. What relationship can we use again? Relating mass and volume. We used it earlier as well. It's density, right? Last time we used density to relate mass and volume, but that was for the overall density. Here we can use the density of solids. So we know that density of solids is equal to the mass of solids divided by the volume of solids. We have the volume of solids, we want to find the mass of solids, but do we have the density of solids? We're not given the value, but we can find it using another relationship, which is specific gravity, right? Whenever you're looking for the density of solid, you can always use a relationship, GS is equal to rho S over rho W. Because GS is always known, 2.65, and rho W is always known. We said here it was 1 ton per meter cubed, right? So that means rho S is equal to GS times rho W, which is 2.65 times 1, which is 2.65. So rho S is 2.65. We know Vs, that means we can find Ms, right? Ms is equal to rho S Vs, which is equal to 2.65 times Vs, which was 6,250, which is equal to 16562.5. So that's your mass of solid. And we said mass of solid remains constant from fill to borrow. So now we can go back to the borrow area, which is what we're actually interested in, right? So going back here, we're looking for VT, and we know MS is equal to 16,562.5 tons. Alright, so now we're again dealing with a volume and mass relationship. So we again have to use a density relationship. So we're saying density total, which we calculated from the test bit earlier, right? Which is 1.9. That's equal to total mass divided by total volume. Now total mass is equal to mass of water plus mass of solid, because out of this, the only two things that have mass are your water and solid. Air, we don't count to have a mass or a weight. And your Vt is what we're trying to find. So rearranging that, we can say Vt is equal to mass of water plus mass of solid divided by rho T. So out of this, what do we know? We know rho T, we know mass of solid. Do we know mass of water? Yeah, how can we find mass of water? Exactly, so we have an expression here, right? We said that mass of water is 0.05 mass of solid. So this is pretty much equal to 1.05 mass of solid divided by rho T, which was 1.9. So that's equal to 9,152.96 meters cubed. So that's the total amount of soil that you have to excavate from the borrow in order to get 10,000 meters cubed in the fill after you compact it. Given that you're adding some things as well, you're adding water to the borrow soil as well. Is everyone done writing that down? Sure, yeah. Can you see that? Yeah. Sorry? Omega, oh, that's just like, this was done online, so you have to use your ZID, but we took omega to be 0. So we're just using 5% for water content.
But I didn't do that in the first one, right?
No, I don't think so. Alright, is everyone good with that? Okay, so we'll move on to part B. Part B is now asking what is the degree of saturation of the fill material after compaction. So now they're asking for the degree of saturation. I'll do it on the next page. Degree of saturation, which is SR, right? And SR is equal to volume of water divided by volume of void. So they're asking you for the degree of saturation of the fill material after compaction. So you've taken the material from the borrow, you've added the water to it, and then you've compacted it in the fill area. And they're asking what's the degree of saturation now. So to get that, you need two components. You need volume of water and volume of void. So looking at volume of water first. To get volume of water, we first calculate the mass of water in the fill, right? And mass of water in the fill will equal the mass of water excavated, so the mass of water in the excavated soil from the borrow, plus the mass of water added, right? Because what did they say in the question? They said the soil from the borrow area is being moistened at 20 kilograms per ton of wet soil excavated. So for every for every ton of soil being excavated from the borrow area, you're adding 20 kilograms of water. So for the mass of water excavated, that's just the mass of water in the original borrow area, right? And the mass of water in the original borrow area we said it here, 0.05 times the mass of solid. So that's equal to 0.05 times the mass of solid plus the mass of water added. So this is a bit tricky to wrap your head around, but they're saying for every ton, which is 1,000 kilograms, you're adding 20 kilograms, so 20 over 1,000, times that. This is for every ton of soil, of wet soil, being excavated. So how much soil was excavated from this borrow area and put into the fill? It was this amount, right? The total mass. And that total mass is equal to 1.05 ms. Because if you think about it like this, imagine you take the soil from the borrow area, you weigh it, right? When you weigh it, you get a certain weight, and that's your total mass, 1.05 ms. And then you think, okay, that's this many tons. I want to add 20 kilograms for every ton of that. So your total mass that you're dealing with here is 1.05 ms. So this is 1.05. So that's the amount of water added. Does that make sense? Yeah? Okay. So if we calculate that, we already know mass of solid from the previous question was 16,562. So if you sub that in, you get 1 second. So that's the total amount of water in the fill, including the original amount of water and the added amount of water. So once you get that, you can find the volume of water using again the density relationship. So we know density is mass over volume. So volume will be mass over density. But what's the density of water? It's just 1, right? When you do with tons. So that's just equal to mass of water. So volume of water is equal to mass of water, which is just 1,175.94. Now we need to do the volume of void. So volume of void, we already got a relationship for this earlier. In the fill, the volume of void was equal to 0.6 Vs, which we derived from the void ratio. So volume of void is 0.6 Vs, which is equal to 0.6 Vs in the fill was 6,250, and that's equal to 3,750 meters cubed. So now we have both the components we need for SR. We can find SR. SR is equal to volume of water divided by volume of void, which is equal to 0.314, which is equal to 31.4%. So that's part B. Anyone have any questions about 2020 question 1? Have you all got that down as well? Yep.
Could you use ESR equals to GS?
Yeah, you could do that as well for the saturation. Yeah. Alright, if we're all good with that, we'll move on to the next topic, which is settlement. Alright, so settlement has 2 components, 1D settlement and rate of settlement. So in terms of 1D settlement, the first thing you want to do is find the change in stress at a certain depth because of a certain applied load Q, right? And there's multiple methods to do this. One of the common methods is the 2-to-1 method. So this one is pretty much saying the load effects increase with depth at a ratio of 2 to 1, 2 vertical to 1 horizontal. And you use this formula for uniformly loaded rectangles and this formula for strip footings. There's also the Borsinas method, so that's just using this formula given a certain values which you have to derive. Strip loadings and circular loadings have these formulas as well. I'm not going to go through these in detail because they're also just in the lecture slides, but these are just the different methods you use to find delta sigma z. You can also use Phantom Sharp or superposition. Alright, so the second part is finding your effective stresses. So your initial effective stress and final effective stress. So what these mean is pretty much when you have a load Q applied to soil, initially what happens is the poor water in the soil takes on all the load. And so if you imagine it in this analogy, when you apply a certain Q, all the water around the soil takes on the load initially. So as soon as the load is applied, the water takes it on. But over time, this load that the water takes on starts to dissipate. And when the excess poor water pressure starts to dissipate, the load starts getting transferred from the water onto the soil. And so you can imagine it as the water kind of flowing out this tap at a certain rate, and then as that water flows out, the pressure starts being shifted to the spring instead of the water. And so the effective stress initial is equal to the effective stress as soon as the load is applied, and the effective stress final is equal to the effective stress at the end of or after all the poor water has dissipated. And what we use these for is to find delta E. So delta E, the difference in void ratio. In order to calculate that, you need certain parameters. You need CC, CR, and sigma dash PC. So CC is the compression index, CR is the rebound index, sigma dash PC is the pre-consolidation pressure. So what these mean is CC is when you draw out the E versus, or the void ratio versus pressure graph, you get something like this, right? And what this means is you apply a certain load and the soil starts getting compacted and compacted and compacted until you let go of the load or you release the load, and then the soil kind of rebounds, right? So the void ratio increases because you let go of the pressure, and the pressure decreases because you let go of the pressure. And CC is essentially the gradient of the component here, and CR is the gradient of the component here of your graph. And we have two different types of soils when we deal with this as well. We have normally consolidated soil and overly consolidated soil. So normally consolidated just means that the current stress it's experiencing is the most that it's ever experienced. Over consolidated means the soil has experienced a greater stress before. And depending on what type of soil it is, the way we calculate delta E is also different. So delta E is equal to CC log sigma dash F over sigma dash I. What this means is, imagine you're calculating delta E, right? That's just the difference in void ratio. So you're pretty much calculating the difference in vertical. That's equal to the gradient, which is CC or CR, times the difference in X. It's like when you do linear equations, it's Y equals mx, right? So it's gradient times your X difference. And that's what this is. Gradient is CC or CR, and your difference in X is equal to log of your stresses in a fraction. That's because this X-axis here is a log axis. So we do log of whatever pressure, whatever value. Alright, and then, so these are the relationships for normally and overly consolidated. And then if your sigma dash PC, which is the most amount of pressure your soil has experienced, is in between your initial and your final effective stress, then you have to use a combination of CC and CR. Right, so imagine first case, overly consolidated soil. That's when the soil has experienced greater stress before. So your sigma dash PC is here, but we're over here because the soil isn't at the peak yet. and imagine it's being consolidated like this, then your gradient will be CR, which is the gradient over here, times log sigma dash F minus sigma dash I. And then when you're dealing with normally consolidated soil, you're over here, right? You're past sigma dash PC. And the gradient here is CC, so that's equal to CC times log sigma dash F over sigma dash I. This will make more sense when we do a question. It's very theoretical right now. But the third case is when your sigma dash I and sigma dash F are less than and greater than sigma dash PC. So that's when your consolidation goes like this. So you're going across two gradients, both the gradients, and so you have to use both the gradients. You have to use CR here and CC here in order to get the difference. And that's what this is. And then after you find delta E, you have to find final settlement, which is equal to delta E over 1 plus the initial void ratio times the height of the layer. So we'll get on to the question. Did anyone write anything down from any of that? Again, it's available on the Google Drive, so don't worry too much about taking photos. But, yes? Yeah, sure. I'm pretty sure it's accessible. Alright, and the rate of settlement is pretty much how the soil settles over time. And so there's two main methods. For that, we use the rate of consolidation for this, so the rate at which the soil consolidates. We can use this one, which is to find the settlement of an entire layer, where we find TV, which is this formula here. Just keep in mind the T here is in seconds, and HD means the drainage path. Drainage path, what that means is, depending on how your soil is, if it's confined or unconfined, your drainage path differs. So confined means that one side is impermeable and the other side is permeable. And your drainage path is the longest path the water takes to escape the soil. So if one side is impermeable, the longest path the water can take is from the bottom of the impermeable side out the permeable side. So the drainage path in a single drainage is just equal to the height of the clay layer. But if you have an unconfined layer, which means that both sides are permeable, this means that the longest path for the water to escape the soil is from the middle, because if you start here, that's still a shorter path, right? The longest path is starting from the middle, going either way to escape the soil. And so the drainage path is equal to H on 2, or half of the soil layer thickness. So once you find HD and CV and T, you can find TV. Once you find TV, you can use this graph to find your degree of consolidation. Once you find your degree of consolidation, you can use this relationship to find your settlement at a certain time. Your other method is when you want to find settlement or pore water pressure at a certain depth. So this one was for an entire layer. This one is now for a certain depth. And what you do, use the isochrones graph, where you have to find Z, which is the depth that you're interested in, HD, which we discussed earlier, and Z on HD, you draw a line across, you find TV, and you find where your Z on HD intersects with your TV, and then you draw a line down. And whatever value you get, that's your consolidation ratio. And you can use that to find the excess pore water pressure or total pore water pressure at a certain point. So we'll move on to a question to apply that. Alright, same thing here, we're taking omega as 0. So we have a uniformly distributed load of 300 kilopascals, so you know that Q is equal to 300. And it's being applied to a 15 by 12 rectangular area, so D is 15, L is 12. The thickness of the sand layer is 5 meters, and the thickness of the clay layer is, we're going to take it as 5 meters as well. So H is equal to 5 meters. The void ratio of the coarse sand is E equals 0.6, so E of the sand is equal to 0.6. And the water table is located at the top of the clay layer. So that's this over here. Undisturbed samples of the clay were taken from the mid layer, and you get essentially this set of data, right? And they're asking us for part A to find the compression index, recompression index, and pre-consolidation pressure. So compression index, that was CC. Recompression, that was CR, and pre-consolidation, that was sigma dash PC. So to find these, what were these when we talked about it earlier? They were gradients, right? So to find gradient values, what do we normally do for linear graphs? So we get 2 points and we find y2 minus y1 over x2 minus x1. So we're going to do the same thing. For CC, first of all, let me give you a diagram to kind of visualize. Alright, so imagine that's your data graph. So you have a set of values at a certain pressure, it's getting compacted, and then you let go of the pressure and so it rebounds, right? Same thing here, you see your pressure increasing, and then it drops down to 20. So that's when it rebounds, when you take off the pressure. And from this we can see certain, like you can see certain properties. So you have CR here, CC here. You'll notice CC is the gradient right before it rebounds. So you want to use the points closest to the rebound point to find CC. To find CR, we want to use the point, or which is the rebound point, so which is the last 2 points. So what I mean by that is to find the point closest to the rebound point, this is right before it rebounds, right? So that's these 2 points here. We want to use those ones to find CC. So CC is equal to, using these 2 lines of data, 0.811 minus 0.722 divided by, remember for pressure, we don't use these values directly, we have to use log of the pressure because the x-axis is a log scale. So do log 1280 minus log 640. Alright. You might notice that these aren't consistent with each other. Like when you say 0.811, the value for that is 640, but we're using 1280 minus 640. The reason for that is because we want our compression index or whatever index to be positive. We can't have a negative index value, right? And when you do logs, if you have a smaller number minus a bigger number, you get a negative value. So you pretty much just think about which 2 points you want to do, and then just make sure the numerator and the denominator are both positive. So don't get too confused about the order that you do it. As long as you use the same points, the order in terms of numerator and denominator doesn't matter. It just has to be positive. Like, you see how I picked these 2 points here?
Yeah.
So if I were to do it in order, it would be 0.811 minus 0.722. That means on the bottom, I would do log 640 minus log 1280, right?
Yeah.
But when you do that, you get a negative number.
Yeah.
And so you want to do it in a way that it's always a positive number. And so it's pretty much always flipped. It's always, if it's this minus this on the top, then it will be this minus this on the bottom. Because that's just how logs work.
Yeah.
Right, and then when you calculate that, you get CC to be 0.296. Doing the same with CR. But CR, we said we have to use the point at the rebound, right? Because that's what this gradient is. So at the rebound, we're now using these 2 values. So same thing, 0.781 minus 0.722 over log 1280 minus log 20, which is equal to 0.3033. Right, and this part also asks for the pre-consolidation pressure, but because this was done online, normally how you find pre-consolidation pressure is you graph everything up, like the official way is you use a Casagrande's method, where you graph everything up and you draw the bisectors and tangents and all that, and you have to find the point of intersection between the tangents and the bisectors. Normally, because this was a online test, they would have been expected to do that by graphing, but because we don't have those facilities, we can just take sigma dash PC to be like an approximated point. So here, sigma dash PC is normally equal to the intersection of these two gradients, right? So around here. And that's essentially the 2 points before your CC value. So I'm gonna take sigma dash PC to be equal to the average of these two pressures, because that's where it's most likely to have the most curvature. That's when sigma dash PC occurs. So don't worry too much about this because this was an online test, and so they were expected to graph it, but for us we can just take it as 240. Alright, so we have that. So that's part A. Part B is saying the water content of the clay sample from the middle of the layer was 30%, so water content is 30%. We're told CV. No, that's later. So 30%, and it's saying estimate the total consolidation settlement under the center of the loaded area using the 2-to-1 method. So we covered this earlier. 2-to-1 method, we said we pretty much use this analogy. Right here. So we were told that B is 15, L is 12. We have a uniformly applied load on the rectangle. And Z, which is the point that we're interested in, is at the middle of the clay layer. So we said the clay layer has a depth of H, which is 5 meters, and so the middle of the clay layer would be 2.5 meters. And so we're taking Z to be 2.5 meters. So when we do that using the 2-to-1 method, the formula for 2-to-1 method for uniformly loaded rectangles is QBL divided by B plus Z, L plus Z. So we know Q is 300, B is 15, L is 12, then we have B plus Z and L plus Z. Alright, and that's equal to 212.81 kilopascals. So that's your change in stress due to the applied load at 2.5 meters in the clay layer. Alright, so now that we've found that, we want to find, our second step was to find sigma dash I, right? Sigma dash I and sigma dash F. In order to find your stresses, you need unit weights. And so we have two soils here, we have sand and we have clay. So you want to find the unit weights of both of those. So for the sand, because the sand is above the water table, we can just take gamma dry, find gamma dry, and then for the clay, it's under the water table. So we have to take gamma saturated. So gamma dry for the sand is equal to GS gamma W over 1 plus E. So this is just one of your relationships that we talked about in the beginning. That's equal to 2.65 times 9.8 over 1 plus E. We were told E of the sand layer, it's 0.6, right? 1 plus 0.6, which is equal to 16.23. And then for the clay layer, we need to find gamma sat. So gamma sat clay is equal to GS plus E over 1 plus E times gamma W, which is So here we don't actually have E of the clay layer. So does anyone know a relationship between E and water content when we have saturated soil? Exactly, yeah, WGS, right? Because we know the clay is saturated, so we know that SR is equal to 1. And we're given the water content of the clay, right? We're given the water content to be, what was it? 0.3, 30%. Yeah, 30%. So we're told the water content, we can use that to find E, so that's 2.65 plus, we're saying E is equal to WGS. Times gamma W 9.8, which is equal to 18.81 kilonewtons per meter cubed. Alright, so now we have the unit weights, we can find the effective stresses, sigma dash I and sigma dash F. So sigma dash I, did anyone want to finish writing anything down? Yeah. All good? Alright, so yeah, alright. So finding the initial and final stresses. Let's start with initial. Initially we have sigma, so effective stress, what do we need? We need total stress, we need pore water pressure, and then we need to subtract them. So initially, total stress is equal to, keep in mind we're looking at this point here at 2.5 meters into the layer. So if I draw that out, alright, so this is 5 meters. And we're looking at this point here. This is sand. It's just flat. Alright, and water table is at the fill line. Alright, so we know gamma here, gamma dry is 16.23. We just calculated that. And gamma sat is 18.81. Alright, so at that point, sigma initial is equal to 16.23 times 5, so that's unit weight times depth for the sand layer, plus 18.81 times 2.5, which is unit weight times depth of the clay layer up to the point that we're interested in. Alright, and that's equal to 128.15. So that's total stress. Now pore water pressure. That's equal to the unit weight of water times the depth, right? Which is equal to 9.8. And here, what's the depth that we use for pore water pressure? 2.5, exactly. Because we only have it below the water table, which is 2.5 meters. So 2.5 is equal to 24.5. So your effective stress is equal to sigma I minus U, which is 103.65. Alright? And for your final, we have to use the change in stress that we calculated using the 2-to-1 method. So final is equal to sigma dash I plus delta sigma Z, which is 103.65 plus delta sigma Z was 212.81. 316.46. So that's your sigma dash f. So now that we have sigma dash I and sigma dash f, we pretty much have the means to calculate delta E. But to find delta E, remember we had three different cases, right? We had normally consolidated, overly consolidated, and a case where your sigma dash PC is in between sigma dash I and sigma dash F. So here, which case do we have? We have sigma dash PC to equal 240, right? So because sigma dash PC is in between sigma dash I and sigma dash F, we have to use the delta E formulation where you use both CC and CR. Because if you imagine it on this graph, sigma dash PC is over here. We started over here and we're going all the way down here. So we're using both gradients, CC and CR. So for the initial part, up until sigma dash PC, we use CR as a gradient. So delta E is equal to CR log sigma dash PC over sigma dash initial. And then for the second component, between sigma dash PC and sigma dash F, you use CC, which is CC log sigma dash F over sigma dash PC. Does that make sense to everyone? Yeah. So using that, CR we calculated to be 0.033 log 240 over 128.15 plus 0.296 log 316 over 240, which is equal to 0.045. So that's your delta E. So once we have that, we can pretty much find your final settlement, STF. STF was equal to delta E over 1 plus E0 H0. E0 is the initial void ratio, which we pretty much already calculated. E0 is just equal to WGS, right? Which is equal to, we said here, somewhere. Yeah, 0.3 times 2.65. That's equal to 0.795. And H0, that's the depth of the compressible layer. So here, the compressible layer is the clay layer, right? So the depth of the clay layer is 5 meters. So that's 5. So STF is equal to 0.045 0.795 times 5. That gives you 0.12 meters of settlement. Sorry? HO, so that's the depth of the layer that we're interested in, or the compressible layer. And here the compressible layer is the clay layer only. We're not considering the sand layer in this case, yeah. Alright, is that all good?
How do we get PC?
PC?
Yes.
Sigma dash PC?
Yeah.
Yeah, that one, like I said earlier, because this was an online test, you had to use like when they give you all this data, you can graph it out and find the intersection of the tangents and all that. But we don't have to do that. Normally they would give it to you if you're given an in-person test.
Yeah.
And so here I just used one of the workshops had similar values, and they took sigma dash PC to be 240. So I just took that, but like it kind of makes sense as well because sigma dash PC happens here, which is the point of the most curvature, and that's right before CC. And so if you take the average of the 2 points right before the CC points, that's 160 and 320. The average of those is 240 as well. So it makes sense in that aspect.
If we go back to the reusability one method,
Mhm.
was there a reason why you predicted the depth of the same as part of the depth?
Yep, so we took Z to be 2.5. That's because the question says we're finding the settlement of the clay layer, and so we only have to worry about the stress imposed on the clay layer. So we're taking everything in regards to the clay layer. Yeah? Alright, so that's the settlement, that's what part B asks for. Part C, how much settlement would you expect to occur after 5 years of application of the load? So this is where you have rate of settlement, right? So you have settlement over a certain amount of time. So what are we given? We're given the coefficient of consolidation, that's CV, is equal to 0.001. Alright, so part C. CV is equal to 0.001 centimeters squared per second. Your time is 5 years. And remember, in the TV formula, your time has to be in seconds. So 5 years, that's 5 times 365 times 24 times 60 times 60. Oops. That many seconds. And you're looking for your settlement at a certain time, so you want to find STT. The relationship we had for STT and STF, which we already have, is STT is equal to U times STF, and U we calculate using the graph to find the degree of consolidation. So STF we already have, U, to find U we have to use this graph right here. And for this graph, we need TV, right? So to find TV, we had a formula for that earlier. It's CV times T over HD squared. And we're given all these values. 0.001 is CV. T is 157.68, 26. And your drainage part, HD. So we talked about drainage part earlier. What would the HD be for this clay layer? So we had two cases, right? We had confined and unconfined. One of them, it goes from the middle to both directions when both sides are permeable. The other one side is permeable, so it has to go through the whole layer to get out of the soil. And so the drainage part, because here one side is impervious or impermeable, we say the drainage path is this entire distance, which is 5 meters to get out of the clay layer. So HD is also 5, and here, because CV is in centimeters, we take HD to also be in centimeters. So 5 meters is 500 centimeters, and so TV is 0.63. And when you go to the chart and you line everything up and you find TV, and you find U, you'll get that the U average is equal to 83% around. Alright, that's from this chart over here. Alright, so once you get that, you can find STT, or settlement at a certain time. STT is equal to U, which is 0.83, times the total settlement, or STF, which we calculated to be 0.12 meters. Alright, and that's equal to 0.0996. Okay, and last part, part D, how much will the total pore water pressure be at point A, located 8 meters below the surface, 3 years after application of the load? So now, we are also dealing with rate of settlement, but we're using the other graph, we're using the isochrone graph. Because it tells you a specific point, Z, and we're also trying to find the pore water pressure. So remember here, we said, to find the pore water pressure, we can use this relationship. So you want to find UZ. To find UZ, you got to use Z on HD, line it up with TV, and find UZ. So doing that. This time T is 3 years. which is equal to 94.61 times 10 to the 6 seconds. So TV is different this time. It's 0.001 CV times 94.61 times 10 to the 6 divided by HD squared, which is 0.38. The Z they give you is 3 meters here, so they're asking you for the pore water pressure at 3 meters below the upper boundary of the clay layer. Alright. So Z is 3 meters into the clay layer, and so your Z on HD is equal to 3 on 5, which is 0.6. And when you use the isochrone graph using Z on HD and TV, you get a UZ of approximately 0.58. Right, and here we can use our relationship. UZ is equal to 1 minus the excess pore water pressure at time t over the excess pore water pressure initially. So keep in mind this is excess pore water pressure, not total pore water pressure. And in the question they're asking us for total. So what you do here is to find ux0 and uxt. ux0 is equal to, so the initial pore water pressure at time 0 is just equal to the amount of load being applied. Like remember when we talked about that analogy with this one? When you apply a certain load, initially it's all taken by the water. And then over time, the water gets dissipated and then it starts getting taken by the soil. And so initially when Q is applied, excess pore water pressure is just equal to Q. So ux0 is equal to Q, and Q here was 300 kilopascals. Alright, and uxt, which is ux at a certain time, we can use a relationship we had here and rearrange for uxt. Right, so 0.58 equals 1 minus uxt over 300. So that means uxt is equal to 300 1 minus 0.58, which is 126 kilopascals after 3 years. So that's the excess pore water pressure remaining. So it dissipated, all the pore water pressure dissipated, and so the pressure on the water decreased from 300 down to 126. Right, so that means U total, because the question asks you for total pore water pressure, that's equal to the excess plus the initial, right? Excess we know is 126. What's the initial pore water pressure? How do we find that? In this clay layer. Yep. Exactly, yeah, so 9.8. So unit weight of water times the depth that you're interested in, so 9.8 times 3. That's equal to 155.4 kilopascals. That's your total pore water pressure. And that's that question done. Anyone have any questions or want to write anything down from previous? Yep. Sorry?
Above C,
Change in E. Part D? D? Are you done with part C? I mean, delta E? Yep. Last page, yeah.
Wait, no, sorry, part D.
Part D.
So it's like the part you just use.
Oh, like the end?
Yeah, yeah.
Okay.
How do you calculate U vectors
T, that was just me rearranging this UZ relationship.
Oh, you're just rearranging that?
Yeah. Yep. Depends like what if you want to find something like CC or CR, you don't really need graphing paper because it's just using values. But if you do have to graph it to find sigma dash PC, they probably will give it to you. Alright, if that's all good with everyone, I'll hand it over to Professor Fanjum for the second half. Oh, you guys get a break as well.
Yeah, Victory Hill. You have to do the math.
You have to do the match.
Yeah. To the drain.
What's your one exam? You have one point.
Alright, once you guys get some food, took a break, just take a seat, I'll get started. So Abhinav, he went through what? I like you forgot. What'd you go through? You went through phase relationships and settlement. I want to be going over 2D. Shh. Hey. Okay. Can you guys hear me? Hello? Yeah? Chris, can you hear me? Alright, so I'm going to be going through 2D seepage and triaxial. I'll try my best to go through triaxial. I'm not too sure myself, but so I'm not sure if Abhinav's mentioned it, but from the past few years, shit's in the way. The past few years, so 2020, 2021, 2022, the main 4 topics that got tested were. Did you mention this? Main 4 topics were phase relationships, I like you forgot, settlement, compaction, definitely triaxial, and 2D seepage. So I'd say these 5 topics are the main topics you guys have to study, alright, for your finals. Yeah, you can expect like 4 or 5 questions. So last year we got a question for each one of them. The phase relationship one was like a bit small, so it's pretty easy. We also got slope stability last year, which I will briefly touch on, okay? Because if you do get slope stability, I don't think they don't expect you to do moments, I'm pretty sure, because like we've got a bunch of environmental students doing this course. and they've never done mechanics in their lives, so moments is a bit of a hard thing for them. But there are like some graphs that you guys would know for slope stability, which I'll go through, I think. So yeah, I'd say main ones to focus on would be phase relationships. Settlement will 100% be there. 2D seepage will be there. Triaxial will be there. These two are a bit of like a maybe, right? If maybe. Okay, cool. So starting off with 2D seepage. Wait, any questions? Nah. Alright, cool. So first question, first topic, 2D seepage. So I've got some diagrams here, straight from the lectures, just to indicate some stuff about 2D seepage, right? So we've got the blue ones, which are flow lines, right? And the flow lines, what they do is they help you visualize a flow channel, right? So pretty much within that flow channel, you're going to have water essentially flowing, right? And you can actually find the value of that flow, right? Using this equation down here, this equation. Q is equal to K times delta H times NF on ND, where NF stands for the number of flow channels. So if we take a look at this diagram up here, the number of flow channels, the way to visualize it, you get one here, 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 and here. So any space between these two flow lines is considered a flow channel. So you'd say that this whole thing is a flow channel, this one here, 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 so on and so forth. Alright? Yeah, that's pretty much the number of flow channels. Number of drops is pretty much you're taking a look at one flow channel. So let's say I'm focusing on this flow channel here, between this flow line and this flow line. The number of drops is just going to be the number of squares within that flow channel. Alright, so you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 drops. So ND isn't going to be equal to 10. Over periods. That's the number of drops. Channels, 1, 2, 3, 4, 5, yeah. The lines. The blue lines. Yeah. Your delta H is given by your total head loss. The way to, I guess, visualize this, the way I like to think about it is like the difference, I guess, in between these two water levels. Yeah. And one more thing I should probably note. We've got something called equipotential lines, the yellow ones, right? So the equipotential lines, at each line, they've got like a different value for head. So do you have a question for that? No, never mind. They each have a different value for head. So it starts off up here with a certain value of head, right? And the reason we call it a drop is because there's going to be a drop in head, right? So the value from this value of head to the next one is going to be like a difference of one drop of head, which I'll show you guys how to calculate. Alright, so if you want to find the, hold on, let me annotate this real quick. Let's say you want to find the value of head. There's something called head loss per drop. I think that's what it's called. So we've got lowercase delta H. This is equal to capital delta H all over ND. Oh, here it is. So this is a head loss per drop. So when you're going from this equipotential line to the next one, it's going to change by the value of delta H. Okay. It'll be easier to actually understand when I explain with the example. Anything else? Flow lines are impermanent boundary, blah blah blah. Oh, also, along these equipotential line, the heads stay constant. So at this point and at this point, the head is going to stay constant. Right? And depending on the value of your flow, your head might change. Right? So because the flow is different down here, the value of head is going to be different as well. Okay, cool. I'm going to jump into an example. So this example, you've seen something very, very similar in the 2020 paper, 2021, 2023, and last year's paper, we had something very similar as well. So you can expect a question pretty similar to this for 2D seepage. So they'll give you something that looks like this. Alright, and first of all, what you have to do is develop a flow net. Alright, so I've developed my own flow net roughly here. Yeah. However, let's read through the question first. So, for a concrete dam with a sheet pile, shown in the figure below, compute the amount of water flowing under the dam. So that's finding Q, your value for Q. Alright, they've given us a coefficient of permeability, 5 times 10 to the power of minus 5 centimeters per second. I've converted that into meters per second. Right, with everything that I'm going to do from now on is going to be meters. So from the get-go, I want to fix up the units. Second question, compute the pore water pressure and the hydraulic gradient at points A and B. So pore water pressure, in the case of 2D seepage, pretty much in the case of anything really, but for 2D seepage, the main formula you want to remember is that U is going to be equal to HP, so your pressure head, multiplied by your, unit weight. That's the formula that you're going to have to remember. Okay? Any questions? Nah. I'll show you guys how to find HP, but one thing you guys should already know, hopefully, is that H is going to be equal to HE plus HP. Okay. There's something pretty annoying about this question, is that you're going to need a ruler. Yeah? So they give us a scale down here, and when you're drawing your flow net, it doesn't have to be 100% to scale, but you're going to be basing all your answers from that flow net. So you're going to need a ruler, you're going to need a pencil. Alright, you're going to have to do some drawing of your own. You're going to have to calculate the distances between that, use the scale. Alright, it's really annoying, but trust me, it's actually not that hard. Alright, with all the questions that you have for the past papers, if you're able to do all 3 of them, or 4, whatever, alright, you'll be fine for the finals. Hopefully. Alrighty. And the last question is the exit gradient, which isn't covered that explicitly in the lectures, so that's why I want to go through it really quickly. Because it is something that they could ask you. Okay, so hint. They've given us a hint, develop a flow net first. Usually it's a question of its own, right? And they said hint, but they tell you you're going to get 5 marks, right? Which is kind of stupid the way they worded the question. Anyways, first of all, I'll try my best to explain this thing here. Actually, what I'll do, copy this, copy it into the next page. Beautiful. So, developing a flow net. So, what we see is that our flow lines are going to start from here, right? Because that's where the water is. Right? The water's going to be flowing from one side to the other, pretty much. Right? And we also have equipotential lines that will connect down to this impermeable rock layer. Right? What we know is that impermeable boundary layer is like a equipotential line as well. Or it connects. No, it's a flow line, but your equipotential line will be perpendicular to it. That's something I forgot to mention actually. Your flow lines and your equipotential lines are going to be perpendicular to each other. Alright, let me scroll up real quick. See over here, they're all perpendicular to each other. Or somewhat perpendicular, right? They're meant to form squares. Right? These are like janky ass squares, but they're going to form somewhat squares. Okay. Actually, no, I'm not gonna. Let me scroll up here. I'll just try to explain with what I have right now because I don't have much time. But the black ones, these are equipotential lines, starting from the concrete dam, going all the way down here to our impermeable rock layer. And then to help me draw my flow lines, I've just drawn like these perpendicular, perpendicular lines, and then just connect them all together. Over here, we don't connect it up here because there's no water here. Right? This is technically a flow line as well. So we'll go all the way around and up here. Yep.
So which one do you go first?
Personally, I like to do the equipotential lines first. Right, it's up to you. Yep. It's like you're meant to do this in pencil, so it's like a trial and error type of thing. Yeah. So when I was doing this myself, it took like 3 or 4 attempts to try and get it to look like this. And then I had to swap some equipotential lines around as well. As long as you make it look nice, then you can like kind of fit things to it. Right. I mean, have any tips? No? Yeah, not really. It just comes with a bit of practice and like a bit of bullshitting as well. Yeah. So what I did initially, it was like one line down here, and then like this, something like that. It looked really odd. And then I kept adding more lines, and then tried to fit my flow line to make it look a bit nice. Right. The hardest part is probably actually drawing the flow net, but I think the markers are quite nice. They'll be like, okay, your flow net looks somewhat right, we'll give you the marks right. Right. As long as your calculations afterwards are able to match what you've drawn, you'll be fine. Yeah. And plus, it's only 5 marks. Right. Everything else is worth altogether 15 marks. Right. If you're able to nail the calculations, you'll be fine. Yeah. Flow net. Anything else that I can talk about? 2D seepage is just a pretty odd topic in my opinion. Like, and you'll see that some of them aren't even like square-like, right? But don't be too afraid, right? If they don't look like squares, it's alright, right? Like you see this one over here, it's not even a 90 degree angle, but it's like close enough, right? That's where the bit of like the art of bullshitting comes in, right? Okay, so first question: compute the amount of water flowing under the dam per meter. So step 1 is to obviously draw your flow net, find your ND and your NF. So number of drops. So I'm choosing this flow channel here to analyze. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 drops. So ND is going to be 13. And the number of flow channels, I've got 1, 2, 3, 4. It's really small here, but it goes up like that. This is a bit of a harder example for 2D seepage, like practicing your flow net. This is a bit of a harder example. Last year, what we got something very similar to this, except there was like an extra like rod sticking out here. So we had one rod here and another like a dick sticking out here pretty much. Alright. In your lecture notes, there's like a bunch of examples that you guys can take a look at. Like if you're able to like somewhat memorize what they look like or take it into your exam, I think you'll be fine. Alright, step 2 is to actually calculate your flow. So we've got Q is equal to K times delta H NF divided by ND. So we've got K, we've got NF, we've got ND. What we need is delta H. Okay? For delta H, you're going to need a ruler. Okay? So when I measured this using my ruler, I got 1.8 centimeters. Right? And using my scale, I know that 1.3 centimeters is going to be equal to 5 meters. So I'm going to have to convert the 1.8 centimeters into, or convert the 1.3 centimeters into 1.8 centimeters somehow. And the way to do that is using this thing here. So I'm pretty much trying to find the value of the head per centimeter. Yeah, this is like the unitary method you guys should know from high school, hopefully. The unitary method. So you just find it for 1 centimeter, and then you multiply it by how much you actually have. Alright. Any questions about how I did this? No. Alright, beautiful. And then I end up getting my delta H. Yeah. And using a delta H, you can find your value of Q. Yeah. Any questions? Rocky, makes sense? Somewhat?
Which forward did you use it to?
Sorry?
Which forward did you use it to?
This one up here.
Right.
So with 2D seepage, if you ever ask to draw a flow net, you're gonna have to use this formula. Darcy's law is like another formula that you guys should know. Q is equal to KIA, where I is your hydraulic gradient. So you can write it as K times delta H over delta L times A. That's the other formula. This is pretty much like a build-up or like a derivation from that original formula, but in the case of 2D seepage. Alright. So over here I've got K, I've got delta H, and I've got NF and ND. If you're practicing this question yourself and you figure out, or you find out that your NF and your ND values are like a bit different, don't stress. Alright, that's pretty normal. During the exam, everyone's gonna have like a different value potentially. Alright, it is possible. Markers know that, and they're like, that's fine. as long as you can show your understanding. Okay, that's the main thing. Make sense? Okay, beautiful. Alright, so part B, they're asking us to compute the pore water pressure. So to compute the pore water pressure, you're going to need HP, so your pressure head, right? And to find your pressure head, you're going to need your elevation head. To find your elevation head, you're going to need a ruler, okay? This is like really annoying, but you're going to have to use ruler all throughout this entire question. Alright, so if I scroll down, so they said for points A and B, you can't really see, but this one's point A. This is point A, oh shit. Point A over here, and then this is point B. So elevation head, you start from datum, right? And you just find the difference in depth, or the height difference. That's literally all it is, right? So pretty much I'm trying to find, if this is my datum, right, because that's where I took my delta H from as well. You can start your datum from up here. The only difference is that your delta H is going to be negative, right? I personally like it when my delta H is positive. This is personal preference. Right. Or you can even start your datum from like down here as well if you want. Yeah. Wherever you want it, just keep it consistent. That's the main thing. Just keep it consistent. Alright, so the elevation head is just this depth here, which I figured out to be 1.1 centimeters. Alright, and then for part B, point B, sorry, it's 1.8 centimeters. Okay. It's a bit to the left, so I could like fit it and not make everything look janky here. But we're gonna have to convert that to meters, right, using our scale. So scrolling down a little bit. What the hell? Okay, so I've got my HE here. So this is my HE. This is for point A, this is for point B. And I'll explain what I've got just above that as well. Okay. So, if you guys remember, as I was talking about earlier, we've got the equipotential lines here, and each one of them stores a bit of head, right? So if I scroll up a little, there's some sort of head for this value, there's some sort of head for this value, head for this value, right? And the difference between those two heads is going to be your head loss per drop, which I explained to you guys here, delta H. However, we know the values of the heads at these points. How about for a value in between? Yeah. So if we scroll down a little, my value of B and my value of my point A and my point B, it lies between two equipotential lines, both of them. So how do I find the head at that point? Yeah? It's just a bit of linear math, okay? So what you do is, because these are technically squares, right? You'd have to find the head difference between here and here. Yeah? And the way you can do that is using a ruler again. Yeah? It's a bit annoying. But let's say we have like H1 here, and then this is H2. So H1, H2. And you're trying to find the head at some point in between. Alright. So it's a bit of linear math. We know the head loss per drop, so we know the head loss per drop is delta H. All we have to do is just scale it down by that length. Okay? Like, if you don't understand it, that's completely fine. Just memorize how to do it. Okay? So here it is. The formula for it, HA, so we start off at our initial head. So the way I'm going to do it is, because I know this head and the number of drops, so 1, 2, 3, 4, 5, 6 point something drops here. Right? Might be like 6.7 drops, I'm not too sure. But you start off at an initial head, and then you're going to decrease the amount of head until this 6 point, and then you're going to find that increment here as well, that difference in head. And the way you do that is, see this box that I've drawn? I think it's a pretty good way to actually explain your working out to the marker, or like to explain it to you guys. Alright, you start off with the initial head, then you have your head loss per drop, and then the location of the drop. What I mean by location of the drop is, we already know that you can have 1 drop, 2 drop, 3 drop, 4 drop, 5th drop, right? But for something in between, the location of the drop might be 2 point something, right? And you got to find that location. And this is pretty much how you do it. So 6, because we're at our 6th drop, and then we just need to find that little distance there. And the way I've done that is I've used my ruler. So I'm like going all over the place right now, but when I measured this distance out, it's 0.4 centimeters. Right? This seems awfully small. I think my scaling just on the iPad is a bit cool, but yeah, it was 0.4 centimeters on my iPad. And then I'm gonna have to scale it down from this 0.6. So if this one whole head, 0.6 centimeters is like a whole head, what is that a little bit? 0.4, right? 0.4, the 0.6, this is your delta H, and then our scale, which is 1.3 centimeters per meter. That's pretty much what I've done to find that location of the drop. It's a bit hard to explain as well, but if you guys just memorize it working out, I think that'll be fine. Yeah. And then it just becomes linear math. So you do your initial minus that change. I haven't subbed it in, but when you sub in 6.185 here, you get 3.627. So that's our total head at the point A. Yeah? Please. Which 1.3? This one? Yeah, so that's just using our scaling. So we know that 1.3 centimeters is equal to 5 meters. Alright? Is that true actually? Wait, let me quickly check that. And we also figured out delta H from earlier as well, 0.533. Oh no, that is correct. Because I guess 1.3 is like your standard. We're trying to figure out what 0.6 centimeters is in terms of meters as well.
Well, we don't have to scale at 6 as well. Why would we
This 6? This 6 is not really a distance. It's like a value for your drop. So like first drop, second drop. So I'm saying it's like 1, 2, 3, 4, 5, 6, and then I have some sort of
6 and a bit.
yeah, 6 and a bit.
Why do you have to scale a bit but not 6?
Because what I'm scaling here is like the okay. Wait, oh, sorry. This 1.3 is not from the scaling. Sorry. This 1.3 should be something from here.
See, I'll think it's 6 plus 0.4 understand.
Yeah, I get what you mean. Maybe that is correct. Where the hell do I get the 1.3 from? 0.6. I would have thought it would be like 0.4 over 0.6. Wait, give me a sec. Let me figure TS out. One second. Oh, bro, what the hell am I doing? Sorry, this is incorrect. It should just be 0.4 over 0.6. Yeah, is that what you're talking about? Yeah. Sorry. That's a mistake on my end. That makes a lot more sense because when I was reading, I'm like, where did I get the 1.3 from? Okay, sorry. 0.6. So you get 6.67. Oh my god. Sorry. No, I just got the working out for this wrong. The scaling doesn't really have what was that? The scaling doesn't really affect your location drop. It's just a bit of linear math. So as I was trying to explain up here, over here, if this whole thing is 0.6 and then this is 0.4, right? I guess that location of the drop would be like 2/3 of the way to the 7th drop. Okay? So that means I won't have to change everything. Lovely. 6.923 minus 0.533 times 6.667. So this should be, sorry? The ratio, which ratio? 0.4 versus 0.6. Yeah, that's correct. But what I wrote earlier was 0.6 over 1.3. So I try to scale it, but the scale doesn't even affect. Yeah. Yeah. Thanks, Loki. 3, 6. Okay, and we already figured out HE. Because I now have H and HE. Because I have H and HE, I can figure out HP, which, when I do it properly, that's 4.23, 7.6, 7.599. So that's my HP, and as you know, to find your pore water pressure, you're going to multiply it by your unit weight, which is 9.8. So if I multiply this by 9.8, 10, I get 74.47. And that's your answer for your pore water pressure. Now, they also asked us to find the hydraulic gradient. Okay, so the hydraulic gradient also requires a bit of scaling because this actually is to do with the length. But your formula for it is delta H, so your head loss per drop, divided by your delta L. Delta L being just the length of that square. Right? And the way you can imagine it is just a gradient, hydraulic gradient, rise over run. Right? So the rise is going to be your head loss per drop, your run is going to be your delta L. Which I figured out for that square, the length of that square is 0.6. So I'm just scaling that 0.6 into meters. So this part here is scaling. And this one is already scaled. I scaled this earlier. So to find delta H, I need capital delta H, which was already scaled from the very beginning. Okay. Any questions, queries, anything? Okay. I'm gonna try and move on a bit faster because I still have to go through triaxial. So I did make another mistake over here. Same thing. I'll try to fix this up. 0.5 over 0.6, which is 4. Let me do it in my head. 4.833. So technically this number should be different. You get 6.923 minus 0.523 times 4.35347. That number will be different as well, plus 6.923, 11.27. And then this number will also be different. 110.446 kPa. Okay, any questions about this one? Hydraulic gradient, pore water pressure, how I found it, what I did. Any questions? Anything make sense? No, it didn't make sense? Yeah. Make sense? Okay, good. Alright. Okay, so now, part C. Part C is asking us to find the exit gradient. Exit gradient is just your hydraulic gradient at your very last drop, I guess. So I'm taking a look at this square at the very end. I'm going to take a look at the hydraulic gradient just for that one. That's your exit gradient. So as your water exits, goes this way, alright? You're finding the gradient for that. Which, they've also asked us to find the factor of safety, which isn't really covered in the lectures as well, that well. So that's why I want to go through it. And also comment on the acceptability. They mentioned it very, very briefly. Okay. They've also given you a W value, which you're going to need to find your quick condition gradient. Okay, so IC. Let's go down a little. So first of all, you're going to need your gamma saturated because in your formula for IC, it's going to be your gamma submerged over gamma W. Oh my god, that's horrible. Wait. Oh yeah, it's just this formula. Gamma saturated minus gamma W all over gamma W. So first of all, I'm going to have to find my gamma saturated. Alright? Which changes with your water content as well. By the way, this formula down here, it's originally 1 plus E, but because as we know that ESR is equal to WGS, and because it's saturated, that means W is just equal to 1. So I've just subbed in WGS. Cool? Yeah? Lucky question? Yeah? Okay, perfect. Okay, now my I exit is, again, it's just going to be delta H over delta L, which honestly just stays the same as earlier because for me, I've drawn it as a pretty nice square, even though it looks like a rectangle. But delta H stays the same, delta L, I found it to be the same as well, 0.6 centimeters. So this. Now, my factor of safety, because they said with respect to quick condition, it's going to be IC over I exit. And the general rule for it is that your factor of safety with respect to quick condition should be greater than 5. In my case, I found out that it's actually less than 5, so it's actually not safe. Yeah? Not safe in the case of quick condition. Any questions? Not. Yeah? Yeah, I will. Yeah. Alright, that's pretty much the whole question. I didn't really get to explain the flow net as well as I wanted because of time. If you have any questions, you can come to me after as well. Yeah? Alrighty. Moving on, triaxial. It's a bit of a deadly one, can't lie. Triaxial is a bit deadly. But all the questions for triaxial were very similar for the past few years. Again, Arman, who really likes to recycle questions, or very similar type of question, just change the value up here and there, try to throw you guys off. But yeah, it's quite similar. By the way, who doesn't have access to the papers? Everyone got the papers? 2020, 2021, 2022? Beautiful. That's good. So, this is a CU triaxial test, consolidated undrained, on a specimen that's saturated over consolidated, so it's OC clay. In terms of explaining the content for it, I'm going to explain it as we go through the question. Okay. So they've also given us a bit of a back pressure, 200 kPa, which will affect your draft 4 TSP, ESP. No, mainly just for ESP. Your ESP is it might even curve a little because of the back pressure. Right? They've also given us some standard values for our friction angle and our cohesion, which is given to be 25 and 10. So originally there was like a bit of a omega here, yeah, but I'm just letting omega be 0. Okay, so omega equals to 0. That's just the angle. Oh no, not an angle. This is a value depending on your student ID that they used to give you when it was online. Okay, a sec. So how much is the pore water pressure reading at failure in the undrained test? Okay, so for the undrained test, just a general formula for triaxial test is this one. What just happened? Alright, here it is. So this, dude, my iPad's not working. Okay, here it is. This is a general formula for your stress difference. Alright. This relates cohesion and also your friction angle. And also pore water pressure. Alright. Another thing to quickly mention is that they've told us that the principal stress difference at failure was 550 kPa. Another word for this, the principal stress difference, is your deviator stress. Anyone know what deviator stress is? Panel? No? Cars, do you know? Deviate somewhat? Yeah. So for your triaxial test, it looks like some shit like this, I think. But then you have like some sort of stress, and then your deviator stress is like something they add on top. Yeah. So that's given by delta sigma. This is sigma 3, and the combination of these is sigma 1. Okay. So when they tell you principal stress difference, this is what they're talking about. No sense? No? No sense. Chris? No sense? Yeah, no. Okay. It's in your lectures as well. Okay. Any questions about this? No? Alright, cool. Okay. So, because we know what, so they've given us this value, they've also given us the value for sigma 3. So stress 3, this is just your all-round pressure. Okay? They might word it a bit differently. They might say the vertical stress, right? That's all your initial vertical stress, something like that. That'll be your sigma 3. So because we know sigma 3 and delta sigma, right, you can find your delta 1. Delta 1 is just plus sigma 3. So your stress difference plus your all-round pressure. So when I did this, I figured out that the value for it is 1050 kPa. We're going to need this later on to find our pore water pressure. Literally for the next part, literally for the first question, you're going to need to find your pore water pressure. So this principal stresses, I've broken it down into total stress minus pore water pressure. So this thing over here is 1 minus U, 3 minus U. The U's actually cancel out because of the minus, right? And I've also subbed it into here as well. But what you get for the inside, you end up getting your U's adding up to each other. So you got minus 2U. That's something to note. Your friction angle, you sub it in. Your cohesion, you sub it in. Is cohesion 10? Yeah, it is. You sub it in. After doing a bit of math, you end up getting your pore water pressure to be 145.74 kPa. Yeah. Questions about this? It's just a bit of subbing in math. Rearranging. Okay, cool. If there's no questions, I'll move on. Plot the TSP, ESP, T minus USP for the CU on a PQ diagram. So this is to do with your stress path technique, week 9 content, so just before slope stability. Alright. Total stress path, E is like your effective stress path, T minus U is your total stress path minus your back pressure. So the U0 stands for back pressure. So you draw your total stress path and you just got to shift it by your back pressure to the left or right. To the left. And so I've done a few initial calculations. So these are some key points on your graphs, right? So your first one is going to be P, right? The actual name for this, I forgot what the exact name for P is, but these are some of the key stuff you're going to have to find. So P, which is just the average of your stresses, then your P dash, which is the average of your effective stresses. 3 is your delta U, so this is your pore water pressure minus your back pressure. So pore water pressure which we actually found in part A, and this is your back pressure. What is back pressure? I cannot tell you, but it is somewhere here. Back pressure of 200 kPa. Yeah. And then the next one you're going to need is P plus delta U. So you change it in pore water pressure. And then finally, you're going to need Q. So Q is on the vertical axis, and P dash is on the horizontal axis. One thing to also note is that your Q is equal to your Q dash. Okay? And the reason for that is pretty simple, is because Q is going to be equal to sigma 1 minus sigma 3 on 2. Q dash is going to be sigma 1 dash minus sigma 3 dash. When you break this down, you get sigma 1 minus U minus sigma 3 plus U over 2, which cancels out, so you get over 2. That's what you get. Cheeky little derivation, but don't worry about it. Alrighty. Is it still recording? Hello. Okay. Now, this is like your general formula when it comes to plotting on the PQ diagram. P dash tan, whatever that value is, then your cohesion, and this. Right? So your tan of the friction angle stands for the gradient, and this is just your intercept on the y-axis or the q-axis. Okay, so plugging some stuff in. This is what my TSP, ESP back pressure stuff looks like. So I'll show you what I started with. So let me copy this. I'll show you how I did it step by step. So I don't think there's time to go to the last question, but there are solutions online for it. So hopefully you guys are able to get a chance to look at it. So this is what I started off with. I'll start off with my TSP. So for my TSP, key values are going to be my P and my P dash. No, it's going to be P and sigma 3. So your initial stress, or your initial vertical stress, before the deviated stress. Alright, so this is that value here. And then this is just your plus your deviated stress. Or this is your sigma 1. Similar to a Moore circle, you're going to need sigma 1 and sigma 3. Okay? But that's your total stress path. Divided by 2. Okay. Now, T minus U0 of SP. This is just your TSP shifted by U0. U0 being our back pressure. So in this case, they gave us a back pressure of 200 kPa. So I'm going to have to shift everything to the left by 200 kPa. Alright, so this value I shifted to the left by 200 kPa. This one I also shifted to the left by 200 kPa. So this difference here is my U0. Any questions? Yeah. How much you go up, they should be equal at all times. But that's the value of Q. Yeah, I was just about to mention that. That value that it goes up by is your Q. Q slash Q dash. Yeah. Now, sorry? Sigma 1 divided by 2. Oh, that's just, wait, sorry. I should probably add it for everything. It's just part of the formula. This is part of the formula for your total stress path. The actual explanation for it. I don't have, I'm sorry. But ESP now. So ESP you're going to need to find. So I've drawn my ESP here. It's a bit of a curve because of the back pressure. Right? However, this value here is given by your... Shit, wait. Let me just color code this stuff real quick. Okay, so I'm taking a look at my T minus U0 SP, so my back pressure 1, and I'm shifting it by minus delta U, and that's going to be my highest point of the ESP, yeah? And this little part here is going to be just U. And we know that this thing over here is going to be minus U minus U0, which we found earlier up here. So you chuck in that point. So before I draw it, I actually just chucked in that point here first. You start off at the 300, right? Yeah, you start off at 300, and it goes like that, somewhat. If let's say you had that value to be up here, then it will look like a curve like this. Yeah. The back pressure causes a bit of a curve.
So how do you know where that value is?
This value here.
Yeah.
One sec. Let me fix this up. Right, it's very good point actually. I've got a mind blank. Wait, one sec. 620. One sec. Jesus. Okay, here it is. This one here. So because this is your effective stress path, right? You start off at 300 and you're trying to find like that effective, oh no, sorry, what am I looking at? This one here, P dash. So your original P is to do with your total pressure, total stress. This P dash is to do with your effective stresses, right? So this is going to be your end point for your total stress point. This is going to be your stress path, sorry. This is going to be your ending for the effective stress point, effective stress path. That sort of makes sense, somewhat. Okay, cool. Any questions about this graph? Yeah? It will be linear, yeah. It will be linear. So an example of that is like here. There's like no back pressure here, so my ESP was like linear. TSP, I don't know what this ESP is. This is for a different question, but this is some old stuff, so I can't really explain it right now. Any other questions? The next recap are actually about to start, so I'll quickly wrap this up. We've got one more thing to go through. It's just this angle. So this is our friction angle. It's like not really a friction angle. It's the slope of your KF line. So your KF line starts off up here and it ends like that at your ESP, right? The slope of the angle, you can just use a formula for it, right? Which is what I showed you guys earlier. So I've just subbed in this to be like 25 degrees or something. Okay. Triaxial, like, it's pretty hard to understand, but if you're able to understand like how to graph, how to use the formulas, because it's just a bunch of formula work. Alright, so the first formula I showed you guys was this one. Yeah, learn that formula. The second formula was these ones, your total stress path formula. The next formula was this one. There's one more formula I'm going to show you guys. Is this one. This is for your Skempton parameter. Shh. Now you're done. Now you're done. This is your Skempton parameter, AF. It's just going to be your difference in pore water pressure divided by your deviated stress, which is given by this. This is a bit of formula work. Alrighty, we're gonna have to end it there because we've got another class for 2303 coming on right after. So I'll end the recording there. But if you guys have any questions.